So our next presentation is Troubleshooting MIPI M-PHY link and protocol issues with Mr. Gordon Getty from Teledyne LeCroy. And Gordon has 15 years of experience supporting protocol analysis tools for high-speed serial interfaces, including MIPI M-PHY, MIPI D-PHY, PCI Express, USB, HDMI, and InfiniBand, which is where Gordon and I met 15 years ago. So Gordon currently has a role of Senior Applications Engineer with Teledyne LeCroy Protocol Solutions Group here in Santa Clara. He has a Bachelor of Engineering in Electronics and Music from the University of Glasgow in Scotland, and a Master's in Information Technology from the University of Paisley in Scotland. Please welcome Gordon Getty.
Thanks, Roy. So, good afternoon, everybody. And these lights are bright, so welcome. I'm very happy to be here at the first MIPI DevCon right here in Silicon Valley. I'm going to talk a bit today about just some troubleshooting techniques that we've encountered with our customers as we do testing for MIPI M-PHY. So the techniques that are in the presentation basically apply to any serial protocol, but I've gone into a bit more detail about mainly M-PHY, unipro, and UFS. And those layers are really what's the key to the debug part of the presentation. So back to the bigger picture, obviously we're here at the MIPI DevCon, and a lot of it's around Internet of Things and things that are connected to mobile devices. So M-PHY is a part of the whole ecosystem designed by MIPI that allows for a low power, high performance interface within the cell phone and tablet architectures. And several of the higher layer protocols sit on top of this M-PHY physical layer. So we're going to talk a little bit how unipro, as an example, fits into that, and how you would debug problems, what kind of things happen when it doesn't work. And it's really, you're basically seeing PC type protocols on a mobile platform. So the biggest difference, now that we say mobile platform, I mean it's in cell phones obviously, but there's all these other Internet of Things devices. So it could be your fridge, it could be your car, it could be the thing on your wrist that counts how much you walk, but ultimately all that's ending up using some kind of processor with interfaces, and M-PHY is one of those interfaces. It is one of the high-speed interfaces. So I think we're all familiar with smartphones that have been growing over the last almost 10 years or so, maybe even a little bit more than that, but 1 billion units of cell phones sold in 7.5 years compared to 21 years for PCs, so significantly faster growth in that market. I think we've seen in some of the other presentations that the smartphone market is flattening off a bit, but certainly the mobile architecture and the ecosystem is still growing significantly. So mobile shipped 4 billion units in 12.5 years. It would take over 30 years at the same rate for PCs. And now we reckon tablets will hit 1 billion in 6 years. So that's huge growth as well. You can see on the growth chart here. So we reckon it's going to be greater than 8 times the size of the PC market. So I think probably everybody here has at least one smartphone. And really the notebook PCs also, in an effort to get high battery length, are really the architecture of those and the notebooks and tablets are becoming very similar. So some trends in smartphone development are, they have large volume, obviously. We're talking about millions and millions of smartphones in a very short period of time. So typically people are changing their smartphone every couple of years at the most. So the design cycles are really fast. There's more demands, much more data being used on the networks. So that requires very high bandwidth, low latency, low power interfaces on these smartphones. I guess this iPad here has a clock on it, so that requires a really big bandwidth, especially when it doesn't start. So it takes 40 minutes for it to finish. But smartphones are basically computers that you have that are in your hand all the time. I think everybody knows that. But other markets are going to leverage this. So this thing that counts the steps on my arm, connects by Bluetooth into my phone, which then connects to the internet. So there's increasing number of things and sensors and information coming through the smartphones and into the infrastructure, all connected to the internet. So there's different MIPI technologies, as you know. I'm sure there's a broad spread of what people are working on here. So they range from the slow speed interconnects, slim bus for audio, SoundWire also for audio, and then low speed chip-to-chip CMOS I/O. And then we go into the high speed. We have D-PHY. Also, we have C-PHY, which has been used, for camera display, and then M-PHY, which we're using for storage, as Perry mentioned in the previous presentation. The development from eMMC to UFS is quite a significant change in storage for cell phones. But M-PHY can be used for multiple different types of protocols, and M-PHY really is just that physical layer that allows those upper layer transports and application layers to sit on top of it. This is just an example here. So we have the M-PHY physical layer, so you could in theory have MPCIe, which is PCIe-based protocol stack on an M-PHY physical layer, SSIC, similar for USB. Protocol, but on the M-PHY physical layer. Then we have this transport, which is done by the MIPI organization for unipro, called unipro, which is a transport which sits on M-PHY, but has upper layer protocol. So this is a little different from something like PCI Express or USB, where the whole protocol stack is defined by the one organization. Perry mentioned that previously. And this is different because MIPI is defining the M-PHY physical layer, and then in case of MPCIe, PCI SIG is developing the upper layers. MIPI does the unipro transport, but UFS is done by the JEDEC organization. So as you saw before, compliance or conformance for UFS is done by UFSA, which is a separate organization from the MIPI organization, but works very closely with it, obviously. Okay, so this is just a quote from the M-PHY specification. What is M-PHY? Why do we use it? So we're facing increasing bandwidth demands. If you think about how much storage is inside a phone these days, I mean, it's not unusual to have 128 gigs or 256 gigs of storage inside a phone. So it requires really fast, really low power, low pin count, and applications that are flexible. So they can be used for different things. So M-PHY, in theory, is a successor of D-PHY. Oops, go back. But really has its own applications. But it requires less pins and then has better power efficiency. So the concepts of M-PHY, we have these terminology. At the lowest level, we have what we call a line, so really differential pair. Then this can be formed into what we call a lane, which is a pair of a TX and RX, and then a sublink being one component of the link, and then at the higher layer, a link which consists of two directions, not necessarily the same width. So the M-PHY allows to have asymmetric links. In this case, you could have two lanes in one direction and one lane in the other direction consisting of a link. Now, the upper layer protocols might specify what is allowed in the lower layer M-PHY. So that, for example, UFS may specify that you can only use a certain number of lanes in M-PHY, although M-PHY's specification allows for more than what UFS recommends. There's different line states, and this is the kind of fundamentals around M-PHY and how it does power savings is fundamentally built as a low power interface. And these line states, we call them, I keep pushing the forward instead of the pointer. Here we go. So we have this, what we call diff-P, which is a positive differential voltage. Diff-N is a negative differential voltage. And then these other states called diff-Z and diff-Q, which are weak zero differential voltage maintained by the receiver, and then this floating voltage, which is called diff-Q. So really when a link is in a sleep or a hibernate state, we'll talk more about those in a moment, it's going to use one of these line states. So effectively, it's using as little power as possible in those states. So the signal amplitudes for M-PHY, it's a low swing DC coupled differential signaling. So it's a little different to likes of PCI Express, which is AC coupled. Typically, this is all very short links inside of a mobile device. So it's not typically pluggable, although as you know, with the UFS card coming about, that's going to be potentially a pluggable version of M-PHY. So the line driver and the transmitter can have two drive strengths. We can have a low amplitude, a large amplitude at 400 millivolts, or a small amplitude at around 240 millivolts. There's different signaling schemes. So M-PHY allows for low speed and high speed. Different modes, high speed's optional mode. It may use a shared clock, or it may have different reference clocks, and it uses a non-return to zero signaling. I'll talk about the low speed and high speed here just in a second. So within low speed, there's a set of gears. These are known as gears 0 to 7, with gear 1 being the default and must be supported. And then high speed mode has currently 3 gears, moving to 4 gears, as I'm sure you're aware. And these are in the multi-gigabit range. So these are right up there with the high-speed protocols like USB and PCI Express. So all modules must support low speed. The default is gear 1, which is in the 3 to 9 megahertz range, so our megabit per second range. And then each gear multiplies that by 2. That's true of the low speed and high speed, as we'll see in a second. There is a gear 0, which is optional, which is below the default speed range, but that is an optional feature. High speed is also optional. If you support high speed, though, you have to support the default gear of gear 1. So gear 2 and 3 are basically double the rates of gear 1. And each of these high-speed gears has 2 rates. There's an A rate and a B rate, and these are for EMI mitigation. So they're a little bit off from the 1.25, 2.5, and 5 gigabit per second rates that you might find in radios. And for regional reasons, different countries use different radio frequencies, so they have different EMI rate series for each high-speed gear. So high-speed gear 1 is either 1.25 gigabit per second or 1.45 gigabit per second, depending on whether it's rate A or rate B. So, and then support for a low-speed or a high-speed gear requires all the gears below it. So if you support high-speed gear 3, you must support high-speed gear 2 and 1 also. So this is just a diagram of the rates that are for low speed at the top here. So these are the gear 1 through 7. The range is 3 to 9 megabit, and these are PWM signaling. And then on the high-speed gears, we have gear 1 A and B, gear 2 A and B, gear 3 A and B. And these are the data rates. So you can see the serial link bit rate is 1.248 gigabit per second for gear 1 rate A. It's 8B10B encoded, so effectively you lose 20% of that. So the 8-bit data path frequency is 124.8 megahertz. And then each of these doubles, so you can see that you've got the 2 rates for gear 1, and then the gear 2 rates are double the gear 1 rates. And then at the bottom here, we have the PWM gear 1, which is the low speed mode. Depends on the upper layer protocol also as to which gears are supported. For example, MPCI or SSIC must use a high speed mode, but UFS can use data transfer and low speed mode as well. So this is the state machine. I think you probably saw this. This is basically from the M-PHY specification. So you saw this in one of the earlier presentations. This is showing that the states that the link goes through to actually do the bursts of data. So if I go here, there's the 2 operating modes, low speed and high speed mode. And there's 2 different, depending on whether it's low speed or high speed, there's 2 different sleep states. So, but data transmission in M-PHY is done in bursts. We have the burst mode, which is where data is transferred, and the save mode, where the link is basically in a sleep state. So it could either be in sleep or stall, depending on whether it's low speed or high speed. So it goes the transition from this low power sleep mode. It goes from diff N to diff P, and then it goes to the burst state, and then once it's finished, goes back to the sleep or stall state. So stall is the safe state of the high-speed mode. So that's the one at the top here. And sleep is the safe state of the low-speed mode, which is here. And then these are the burst modes, the high-speed burst or PWM burst for the low-speed modes. This is just a kind of high-level overview. It doesn't go through all the details, but gives you an idea. So beyond the sleep and stall mode, we also have the hibernate mode, which is an even lower power state, where the link's in the diff Z state. So it uses low power. So data bursts, whether it's in low speed or high speed mode, follow this process. So there's power saving states in between each of the bursts. So we start in the stall or the sleep state, then we go through this prepare state, then we have a sync if it's in high speed mode. Then these are basically 8B, 10B symbols, so the marker symbols. We have some filler potentially, then the data, the end of the frame, or the tail of burst, and then it goes back to the sleep mode. So the burst state starts from save, whether it's low speed or high speed, transitions from diff N to diff P, going through this period of prepare, generates then a sync pattern so the receiver can lock onto the signal. It sends marker 0 here, which is followed by the data and also could be fillers. So the marker 0 is used for the receiver alignment. It's going to be K symbols in the 8B, 10B symbols, kind of like skip ordered sets are in PCI Express. And then you end with this tail of burst symbol. Remember, this is all the M-PHY part. This is not the unipro or UFS at this stage. So Hibernate is an ultra low power consumption state, but it does maintain the configuration setting. So once the link is up and has configured each of the devices, then it keeps those even although it goes to this low power Hibernate state. So modules are required to support Hibernate. In Hibernate, the transmit will be in a high impedance state, and the receiver will hold the line at diff Z state like I showed earlier. So when you enter Hibernate from low speed or high speed mode, then the protocol, so the upper layers, mustn't request that the module exit for a certain period of time. So it doesn't make sense if you go to a Hibernate state and then just stay there for a short period of time. You don't end up, it's not useful for a power saving, so it must stay in for a minimum period. And those are defined. The calculations are based on the implementation though, so you can see that in the spec. Okay, so that was a very quick overview of M-PHY. So that is only covering the physical layers, and then what I'm going to talk about are the layers that are above that. And these layers are very important as to whether something's going wrong. So if you're trying to debug a problem with unipro or with MPCIe or M-PHY, which layer causes the problem? So is it a physical layer problem? Is it a signal integrity problem? And how does that show up? So with a unipro problem, what would you see in unipro context if you had a signal integrity problem? You may see nothing, or you may see errors happening randomly through the traffic. Or is the problem really something that's happening at the upper layers? Is it a software problem? Is it related to flow control or buffering of the packets? That's where you always want to define where that is before you try to debug the problem. So this is a protocol stack for unipro. So this is defined by MIPI organization. So the medium in our case here is going to be M-PHY. So that's the layer 1 is defined as M-PHY in this case. So, and unipro is a specification that defines the data transfer between two devices. So it defines data structures, frames, and information about things like flow control, error handling across a link. The current version is 1.61 for unipro, and that mandates that you use M-PHY for the physical layer. So the physical layer, layer 1, is M-PHY. The next layer up is going to be layer 1.5, and this is a kind of intermediate layer, which we call the firedoctor layer, and that's responsible for taking out the, abstracting the details of the PHY from the upper layers. So the firedoctor provides bandwidth scalability by supporting up to 4 PHY data layers per direction, but the upper layers don't care about that. This is all managed by this firedoctor layer. So when you have multiple lanes, they're assumed to have the same capabilities, and the lanes should all be in the same state. So layer 1.5 automates a significant part of the requested steps for power mode control. So things like when you come up in low speed mode and you want to change to the high speed mode, this is managed by the layer 1.5. I'll show you an example in a second of what that looks like. So it uses this protocol called PSEP, Firedoctor Control Protocol. And these frames, which are created at this layer 1.5, are multiplexed into the symbol stream. So you'll see them in a second. Things like the link capabilities are advertised here and negotiated here. So these are very low-level frames. They're just above the level of M-PHY, but it's part of the unipro protocol. So there's a difference between power states and power modes as well. So an application can set a power mode, but it can't define a power state. So the power states are the M-PHY states at the lowest level. So depending on the mode, the layer 1.5 manages this power request between the upper layers and the physical layer. So here's an example, a trace of a system that's coming up. So these are physical layer and layer 1.5 capabilities that are shown in the PSEP frames as the link comes up. So these are capabilities, and this is what kind of capabilities are in there. So which high-speed modes does it support? You'll also see, does it support scrambling? Which rates does it support? That kind of stuff. So this are, you can see there's one in each direction, the upstream and the downstream. Here's an example of a power request. This is another type of PSEP packet, or frame. So this is requesting to go to a higher power state. In this case, it's going to rate B, and it's going to TX gear 1, so rate 1B, and it's also going to be fast mode, so not fast auto. It says, I think scrambling is not requested in this case. I haven't seen many implementations of scrambling being implemented in M-PHY yet. So remember, this is a layer 1.5 frame. This is still very, very low level. This is where the power mode change is initiated. So you can see it's happening at the low speed mode, and it's requesting to go to a higher gear. This was a real capture from a real system. So next layer up is layer 2, that's the data link layer. The data link layer is managing the reliability of, or it provides reliable links by making sure that frames get to the other side of the link properly. There's a CRC check, and also provides for flow control. So it can also have multiple types of data traffic. It's multiplexed between those. So, and then a frame at layer 2 looks a bit like this. So they all start with the same kind of header, and then the layer 2 payload is in here. So this is layer 2. So this is really your flow control and your ACK and NACK mechanism, making sure that packets or frames get across the link intact. The next layer up is the network layer. That's not really used too much at the moment in Unipro, but it has the concept of a packet, and the idea would be that you could route it across networks up to 128 devices. So the next layer up is going to be the transport layer. So this is the highest layer that the Unipro spec defines. And that allows physical packets between two devices to go back and forth. So ultimately, this is a higher layer protocol driving it, if you think about it. So you have some SCSI command at the top level. It has to be put into packets that can be transferred across the link using this Unipro transport. So Unipro transport layer 4 does support multiple bidirectional connections. And it basically guarantees that the data sent over a single connection arrives in the same order that it was sent. Something that's interesting in Unipro is preemption. So this is where a frame can be broken up. So in order to reduce delays of high priority frames, so you could have a frame going down the line, and then another higher priority frame can intercept that. So it basically breaks the first frame. So it can do that. This is known as preemption. It's optional, but the receiver's always required to support it. So what it looks like is you have this start of frame concept. So you have part of the frame here. You can see the BC is the marker at the beginning of the frame. And then we have this continuation of frame. So we have start of frame and end. But we could, if we have continuation, it's like the start again in the middle of the previous frame that's been preempted. So this particular frame has two fragments, one that starts here and then another fragment that goes together. So the frame is not necessarily contiguous on the link. So this makes it a little tricky when you're trying to debug also. So UFS, as you heard from the previous presentation, is the Universal Flash Storage Protocol. It's written by Getty. The current version is 2.1. And it's a Getty standard. It's primarily used in mobile systems, as you know, and it's really a development from eMMC, or a replacement for eMMC SD cards that we see. So MPHY and unipro are specified as the transport and the PHY for UFS, and it's basically built around the SCSI architecture model. So why would you use UFS? So it's going to be faster, higher performance, more efficient, more responsive. So like I said, when you have huge amounts of data on your phone, if you have HD videos that you're trying to store on your phone, you want high performance, but you don't want it to kill the battery. So also just loading apps, making things faster, more responsive to use, UFS is going to help that. Again, lower power. It takes advantage of using M-PHY for the physical layer, which is inherently very low power. It's scalable and small also, and it's easy to build in with the technical infrastructure because it uses the standard SCSI model and SCSI framework. So software at the higher levels just sees them like SCSI devices. So it makes it very easy to integrate that into a system. And you can just take advantage of the bandwidth that's provided by unipro and with M-PHY. So this is what the UFS architecture looks like. This is just taken from the UFS spec. So here we have the M-PHY physical layer, the unipro transport, and then this interconnect layer between the UFS and unipro. And then we have the UTP transport protocol layer, and then the high-level command set for SCSI. So for UFS, the UFS interface can support multiple lanes. Each lane is a differential pair as per M-PHY. The basic configuration is based on one lane in each direction, but you can also support 2 lanes, so giving you more bandwidth. So the links for UFS must be symmetrical. So although M-PHY allows you to have asymmetrical links, UFS will actually allow you, it must be symmetrical. Kind of makes sense if you think about it as a storage protocol, so you have data going in both directions. It's different from a camera, which is mostly one direction, or a display, which is mostly one direction. So it makes sense that they define that it should be symmetrical for UFS. So the application layer of UFS consists of the UFS command set layer, or the UCS, the device manager and task manager. So the upper layers are going to handle things like read commands, write commands. And UFS is designed to be protocol agnostic, but this version basically uses SCSI. So like I said, it makes for easier integration because of the higher level software is going to already know how to talk SCSI. So if you took a trace capture, what does it look like? A SCSI command, it's going to look like a read 10 here, and then what we show here is the components of that command. So these are all made up from UFS or MIPI frames, unipro transport, and then the UFS components shown here. So we have the read command and then the data transfer. So we can see the opcode here is a 28, so it's a standard SCSI opcode for the read command. The write command, just another example, so write 10, In this case, we have the data going in this direction. So you can see in the read command, the data transfer is in this direction. This is the command and the data. And then the write command, we have the command and the data in the same direction as the command. So we have the host and device concept here. Okay, that's the fastest UFS and unipro overview ever. So the next thing is about how do we debug these problems. So there's various things you want to think about when you're doing this. Like I said, it usually goes back to figuring out which layer the problems are happening at. So once you know what that is, if you have a signal integrity problem, don't try to figure out what's going on at the SCSI level or the UFS level. It's not going to work. So always verify that your signal integrity is good, first of all. Figure out the right tool, so you don't use a hammer to screw in a screw. What I mean there is don't use an oscilloscope to try and do a software debug. Don't use a protocol analyzer to try to look at signal integrity. So use the correct tool. And then once you've got the correct tool, try and figure out what's causing the problems. So what's challenging with M-PHY is, compared to other protocols like USB or PCI Express, is it typically doesn't have a connector. So you're dealing with chip-to-chip systems, often very small and a very tiny PCB. Some development systems may have SMA connections, so that makes it easier to access it, but the primary challenge is to get access to the link. How do you connect a probe to it? So you could have SMA, you could have a multi-lead or a flying lead type solder down probe, potentially a mid-bus type footprint, but realistically the size of the systems is not really going to allow that. As I said before, check the electrical before you do the physical, before you try and do any protocol. Then try and use the right probe. So if you're using a protocol analyzer, it's more than likely you're going to have to use a solder down probe at some point, especially on a production or a late prototype. So this would allow you to connect directly to the link. And remember, you have to do that in both directions. So if you're looking at electrical, you're looking at each side independently. If you're looking at protocol, it's the interaction between the two sides. So you need to make sure you probe both sides of the link, otherwise you'll only see half of what's going on. So obviously SMA, another option here, may be available. So, like I said, use the correct tool. Is the problem related to signal integrity? If it doesn't work, so if you don't see the storage, for example, in UFS, are the devices physically connected to each other? You know, can one see the other? If they can see each other and it's working, then it may be that it's not a connection problem, but it is actually a signal integrity problem. Do both sides have compliant signaling? You would use a scope obviously to verify this. So next thing is, if the two devices see each other, can they see each other and does it actually work? And is the data rate as is expected? So for example, you know it supports gear 3B, but it's only operating at gear 1B. So what you can do is you can look in those PACP frames that I showed earlier and say, okay, is it trying to go to the higher speed? Or is it going there and it's falling back to a lower speed? Again, this could be an electrical problem. Now, it could be that it's operating at the lower speed, but it's actually still functioning. So at the higher level, you can see it works, but you may not get the performance that you're looking at. So in that case, you're going to use a protocol analyzer, not an oscilloscope. So which layer is causing the problem? If you're having problems, they could be related to performance. It could be reliability problems. You may see errors on the link. If the thing crashes, is it something that happened on the unipro link that caused it to crash? That's what you need to determine. If it crashes, what was the last thing that happened before it crashed? And that's where you use an analyzer to look for that. Is there actually a signal present? So you connect up a protocol analyzer, you think the thing's working. Is there actually a signal going between the two devices? So what you can do is use a scope to figure out, is there something there? This is something that is, particularly for M-PHY, because it is embedded, we don't know what the signal is. It's not a connector that has a standard pinout. So potentially you plug in your analyzer like this, you connect up to the DUT and you see nothing. So what happens in that case? Well, you could just take the output of the probe and connect it to an oscilloscope instead and see what the signal looks like. If the signal is too small, then it's no surprise that you won't see anything. Again, it goes back to which layer. So if the electrical part doesn't work, then there's no way you're going to debug any protocol stuff. If the electrical stuff is marginal, it may work, but it may not work in the way you might think it would. So what would you trigger on? So it depends what you're trying to look for. So for example, if it's not performing the way you would expect it to, the trigger condition could be to look for a PACP, a power mode change, and see if it's requesting to go to the higher power state. It may be that you're looking for a software problem where there's you're looking for a SCSI command to happen, so that may be your trigger. So if it's a protocol issue, you need to look at the upper layers. So electrical could be fine, everything works, but then you get this strange behavior in software. So you may want to use a SCSI type trigger to look for it, for a certain command. I think I started this a little bit late, but that's right about 40 minutes. So that's pretty much all I had to say. We have some more in the exhibition hall. If you have any questions, I'd be happy to answer those just now. We also, I think, have a break coming up in a minute as well, so I can stay around for a little while. Any questions?
Everybody knows how to debug their UFS device now.
Or nobody's done it yet.
Oh, that was it. All right.
Okay, well,
any questions?
Yeah.
Okay.
No questions. Thanks very much. I'll be here for a few minutes. If you want to come up and ask questions, that's fine too. So. Okay. Well, thank you very much.